This video will involve free body diagrams. Basically, what a free body diagram is you want to reduce the object that you're interested in analyzing to either a box or a bar. So in the end, we want the problem to look like a box with a whole bunch of forces coming out of it. Could be going in any directions. Or a bar. And the reason that we would choose a bar would be because the forces don't all come out at one point. They might be coming out like this or whatever. So how do you know whether to do a bar or a box? Well, you'll just sort of get the experience of these examples that I'll give you. And basically, if you can reduce the object to all the forces coming out at one point, then you're going to use a box. So let's just do a whole bunch of examples. So we'll just start with somebody standing on the ground on 2 feet. Okay, so this will be our stick man. So what are the forces acting on this person? Now, the bar example, I mean, certainly this person looks like a bar, but if he's just standing there, there's not going to be any kind of rotation. So this can be reduced to a box. So the center of mass of the person has the force of gravity. So you always have the force of gravity on the object. We're not going to have any objects that don't have forces of gravity on them. And then remember, it has to be contact forces happening here on the floor. So standing on 2 feet, one foot has a normal force on it, Fn1, and the other foot has a normal force on it, Fn2. And you could easily be standing on ice, and this would be just fine. So there is no friction here. If you suddenly made this floor at an angle, well, then you would need friction to stay on it, because if it was ice, you would slide. Okay, so that would be a box. This person would have 2 normal forces from each foot, which may or may not be equal. It all depends how equally you stand on your 2 feet, and then a force of gravity. We're not going to worry about what the values of these forces are or whether they balance right now. We're just worried about identifying the forces. Now, if you were standing on 1 foot, then clearly, now you wouldn't actually be able to stand like that, because if the force of gravity doesn't fall over the point of contact, well, then you're going to tip over. So your foot would actually have to be under your body here like this. And then the contact force, once again, it would just be a box, but there would just be 1 from 1 foot, and that would balance the force of gravity. Okay, so somebody just standing around, you reduce your body to a box. Now these forces don't necessarily have to be equal. If you were jumping up, so let's say you were in a crouch and you were jumping up. Well, you still have the same forces. You still have a force of gravity here, and you still have a normal force to your feet. And we can actually reduce both feet to 1 blob here. So you would have the normal force from the feet. And in this case, actually, that normal force would be bigger than the force of gravity. And that's the imbalance that would cause you to jump up. So you do not always assume that the normal force equals the force of gravity. It all depends what the body is doing. And the way you can think about this, if you're standing on a bathroom scale, just imagine standing on a bathroom scale. Can you vary the reading on the scale? Like, what can you do to make the reading on the scale change? Well, you can start jumping around on that scale. If you crouch and then push off the scale is going to read a bigger number than if you're just standing still. And then if you're standing on the scale and you sort of just let your weight fall a little bit, bend your knees, let your body go down, you can actually reduce the reading on the scale. And so it is actually the normal force is what the scale reads. It is not reading your force of gravity. You can't do anything about changing your force of gravity. That will always be the same. But depending on how you move your body up and down, the normal force will change. And then, like I say, the normal force is the scale reading. Okay, so now if we were lying down on the ground, would we make ourselves a box or a bar? Well, if we're just lying there, we can draw through the center of mass of the object, the weight, and then through the center of mass, the normal force. Now, in reality, we've reduced the force of gravity to one force at your center of mass, but in reality, you've got forces of gravity on your head, and any point of contact has a normal, but gravity is everywhere. It doesn't matter whether you're on a surface or not. And so what we effectively do, all these little forces of gravity, we reduce to one force through your center. And similarly, every point of contact with the surface, you would have little tiny normal forces. Now, if you're not touching the surface, you don't have a normal force. You might have one at your shoulders, and then maybe one, on your back, and then your feet, hips, whatever. But we would just reduce that to a box. And if you were lying on a bathroom scale, that normal force would be the reading on the scale. But if we're not lying flat like that, what if we were lying on a stack of books here and here, and we had to really use our core to support our body like this? And that'd be pretty tough. Now, this would definitely be a case where we would have reduce our body to a bar. And we would have the bar having just these 2 points of contact. So this would be our body. And we would have two different forces, depending on where our center of mass is relative to the distance between these bars. These may be different forces. Now, our gravity vector still goes through our center of mass here. And it turns out that these Fn1 and Fn2, these contact forces, are not equal to each other because this force gravity is not in the center of our body. So that would be a case where we would want to reduce ourselves to a bar. Similarly, if you were leaning against a wall, people do a calf stretch. You see people leaning up against a wall like this to stretch their Achilles. Well, this would be a case where we would want to reduce ourselves to a bar as well. So what are the forces on our body? Remember, we're not worried about the wall or the floor, but we're worried about the body. And so at the wall, there would be a normal force due to the wall. We would still have our force of gravity coming out of the center of our body. And remember, we have to keep our body rigid here. If we start sagging our hips or pushing our hips back, that changes everything. That reduces us to 2 bars, or however many segments that we're moving about. But we want to keep this simple right now and make sure we stay completely rigid. And so at the ground will always be pushing up on us. And now, imagine doing this on ice, what would happen? Well, if this was ice, your feet would flip out to the left. And so friction must be keeping your feet there. So this would be the force of friction. And so if we reduce our body to a bar here, there would be the wall force, there would be the normal force due to the floor, there would be the friction force, and there would be the force of gravity. So that would be F wall, F normal, F friction, and F gravity. Now, in physics, we leave it at that. In biomechanics books, they often combine this. And they would say there is a ground reaction force at the ground. So they would take the sum of these two forces. Now, it does not necessarily lie along the bar. It could be at any angle. It depends what the coefficient of friction is. And so this normal and this friction, we would just leave it at that for physics. But this combination, the sum, the resultant, biomechanics books call this the ground reaction force. Okay, it's not an actual force, it's the resultant of two actual forces. Okay, so you will see that in lots of biomechanics books, and sometimes they'll do it wrong, ground reaction force. Sometimes they'll call Fn the ground reaction force, and then I'm not sure what they do after that, but there's no real reason to do this, but you will see this in biomechanics books. Okay, now how about friction? Remember, if you have a box, let's just take it a box, forget our body, just sitting there. There's no friction on that box, okay? If that's a horizontal surface, there's a normal and there's gravity. If you want to introduce friction to this situation, you have to pull on the box. So friction has to work against you pulling on the box. So say this is an applied force. As soon as you start pulling on the box, poof, friction appears. And friction will try to resist that motion. So you would have a force of friction. And we've already looked at the inclined plane, so I'm not going to go through that again. There's a whole video on the inclined plane. Okay, let's look at running now. So what's the situation with running? And when you're running, you have to consider air resistance. Now, to actually come up with a number of newtons for air resistance is incredibly difficult. Air resistance depends on the surface area, the frontal surface area that's trying to move through the air. It depends on the speed. And so at low speeds, air resistance isn't that high, but as soon as you start increasing speed, it increases as the square of the speed. So in a 100-meter sprint, about 10% of the energy is used to overcome air resistance. But for cyclists, it's because the speed is so much higher, it's almost 90% of the energy. That's why drafting is so important in cycling. And so let's look at the different stages of running. So taking off from the sprinting blocks, the sprinting block is a huge advantage to the runner. So remember, we're interested, now we would just be interested in this leg. So say we're just going to reduce this leg to a little box. We could reduce it to a box. And then that will translate up through your body as your muscles keep your body together, basically. So on your foot is a normal force due to this starting block. And that is always perpendicular to the surface. Now, there are two components to that now. It would have a horizontal component. Remember how we broke forces into components? And so this is a case where the normal force, this is the block pushes on leg. This would be the horizontal component, the X component, and this would be the vertical component. Now, the reason this is such an advantage is because look at this. You actually have from the block this force moving to the right, which is the direction you want to go. That's going to help you move to the right. So that's how it works with the starting block. There's just one force due to the block, and that can be resolved into these two components. Now, so now let's assume you're running along. And you're still leaning quite far forward here. What are the forces on your body? Okay, you always have the force of gravity coming out of your center of mass. So that's there. And now you're running along, you don't have the block, so the force due to the ground is vertical. That's all the ground can do is push vertically up to keep you from falling through the ground. And now, remember, if it was ice, this foot would flip out to the left. So friction must be to the right. And that's why you want to wear good shoes that have maybe little spikes in them to increase that friction force. Now, you can't neglect air resistance here. You will have air resistance, and we'll just put it right up here. Okay, so this normal force is exactly going to balance that force of gravity, and you don't want to have your center of mass violently moving up and down. That's just a waste of energy. But the forward propelling force is this friction force down here. And air resistance is simply slowing you down. And so initially, the beginning of a sprint, and you're accelerating, this force of friction is going to be bigger than that air resistance. But at some point when your speed is just, maybe you're getting tired, you're not pushing against the ground as much, the air resistance is going to equal this force of friction, and you will no longer be speeding up. Now, as you continue, if you now plant your front foot as you're running along, and this is why you don't want to be a heel striker and get that foot too far forward of your center of mass. If you put it down just nicely here, the force, you're still pushing off the ground. Your body is rotating over. You're still pushing off the ground. You still have a little bit of a force of friction here. So you're still, that foot is still underneath you, and you still have air resistance here. And then the normal and gravity are always there. So at this point, if the force of friction equals your air resistance, you're not accelerating there. You're just cruising, maintaining your speed. Now, and as you get more and more tired and this force of friction becomes less and less, the air resistance starts to slow you down. Now, if you finish the race, I mean, you always want to have this force of friction forward. You always want something to be moving you forward. You never want to be planting your foot that's going to create friction in the opposite direction to slow you down. So this, you're still moving this way. You're still moving this way. But let's say now you want to stop. Well, then you're going to lean back, throw your foot down such that your body's way back here now. And now think of which way your foot would slip out if that were ice. It would slip out to the right. So clearly friction is left. And this is definitely going to slow you right down. And that's what you would do to actually stop. Okay, so this would be slowing down this way. Okay, so that's what's going on when you're running. Let's do another example of a push-up. So what are the forces on you, and what do you do with your body when you're in a push-up position? So this would be, you'd want to reduce your body to a bar, not a box. Okay, so let's have your hands out here, your feet here. Okay, so what's going on? Gravity, always gravity through the center of mass. Whether you're a bar or a box, you put the gravity through the center of mass. Now at your feet here, the floor, if you have contact with the floor, you will always have a normal force, always pushing your body away from the floor. Floor does not suck you in. So your hands would have a contact force as well. Normal force, call that the normal force. Now the question is, do you need friction here? Well, it all depends. I mean, if you're a phenomenally strong core and you can hold your body like that and balance with those upward forces, now you don't need friction. But most of us, if you've ever tried to do a push-up, when you have like a barbell or, you know, one of those rolly things on your hands and your feet, you notice how difficult it is to maintain that position. So normally there would be friction, and the friction would be on your feet this way and on your hands this way. And those two forces of friction, if you're not moving anywhere, would have to equal each other. Okay, so that would be a case where we would just want your body to be a bar. And on this bar, we could move, we would put a force here and here, and here, and here, and here. And then we could look and see what's going on with your body as far as motion or rotation or whatever. Okay. Now, sometimes it's confusing what it is we're analyzing. So what about if we have someone holding onto a barbell? So let's say this person has this giant barbell in his arms here. So what is the free body diagram? Well, it all depends. Are we interested in the barbell? This is the barbell. Or are we interested in the person? And they are separate objects. So usually in this, well, it depends. It depends what the question is. The question might be, what are the forces on the barbell? Is the barbell going to tip? And is the barbell being held horizontally? But then it might also be like, what are the forces through your body to hold up that barbell? And so If we're going to do the barbell as our object, then you would reduce it to a bar. And what are the forces? Well, there's the force. We would assume that this barbell is symmetric so that the weights on either side are the same and clearly the bar is uniform. So we could reduce the force of gravity on the barbell to one force at its center of mass. Now that doesn't matter whether this barbell is being held horizontally or not. That is where the force of gravity acts. Now what else? That's clearly, if that's the only force, the thing would fall down. And so the point of contact between the two hands would be an upward force holding the barbell up. So this would be the force from the right hand of that person or the force from the left hand. So I guess we would actually be looking at the back of this person if that was the right hand and the left hand. Okay, so that would be the barbell. Now, if we were interested in the person, what's going on with this person? We could reduce this person to just to a block. Okay, so there's the force of gravity of the person in himself. Now, which way is the force due to the barbell on this person? Well, obviously it's pushing down on the person. The person, these forces, this is the person pushing up on barbell, holding up the barbell. The barbell in turn is pushing the person down. So this person, which you'd assume the barbell is huge, this would be the force of gravity of the barbell on the person. And then that has to be counteracted by the force from the floor. That would be the normal force. Now this would be from both feet. What's happening here? Both feet. If you stood at 1 foot, well, that would be phenomenally difficult, but that would have to be from both feet. Now, depending on whether this person is like squatting up from the ground holding this barbell or lowering it to the ground or just standing there, these two would never change. So these don't change. But this could certainly change depending on the motion of that barbell. Changes depending on motion. So lifting the barbell from the ground up is going to require a lot bigger force than just letting it drop down. So that normal force, which you have to generate by pushing against the floor, by using all your muscles, contracting your muscles, that will change depending on the motion of that barbell. Okay, oh, something else. If you just jump out a window or jump off a cliff and you're falling through space, that's your free body diagram. This would be just a block. There would just be the force of gravity, and then there'd be the force of air up. Now, in most physics courses, we completely neglect the force of air, and we just do free fall problems, they're called. This is free fall, looking at the force of gravity. In biomechanics, this air resistance force is going to be a little bit more important, and we will include it for many of the problems, but most likely you'll just be told, like this is 10 newtons or 30 newtons or something. So this is the free fall, it's called. Nothing else acting on you. It doesn't matter if you were to jump off the ground and be in midair on the way up. So this is free fall going down. But you could jump up and be moving up in free fall, in which case force of gravity is always down, never changes. But if you're moving up, so this is if you're moving down, air resistance now would be this way. This would be if you're moving up. So that'd be if you had to jump off the ground and that little bit of time you're actually in the air going up. It's still called free fall though. Air resistance just flips over because it's slowing you down. Air resistance always slows you down. Okay, now another example, they can get quite complex, these. So let's say now we're just worried about your forearm and you're just holding your forearm. So here's your bicep muscle, your hand, elbow. There's your arm. This is supposed to be your arm. Okay, now what is the free body here and what are the forces? The free body is going to be, we're going to reduce it to a bar, this, just the forearm itself. Okay, so the forearm is what we're interested in, and it becomes a bar. And it can get quite complex. So I'm going to draw it down here quite big. So what are the forces acting on your forearm? Well, let's put gravity in. Now, your forearm, let's say, well, we could actually put a little weight here. How about we put a little weight in your hand? A little, so you're holding a little dumbbell here. Okay, so we've got the force due to the little weight dumbbell acting at your hand. We've got the center of mass of your forearm, which tends to be a little bit closer to your elbow than, it's not in the middle, it's a little bit closer to your elbow. So that's the force of gravity of the whole forearm. And you put that at the center of mass. And that is something that's determined empirically, and everybody's a little bit different. So, whoops, I put forearm. Now, what are the other forces? Well, you have the brachioradialis here, that's holding, so your wrist doesn't flex. So that would be a muscle force, and we draw it like this. So that would be brachioradialis. And that would be at a very small angle. Remember, that muscle has to be inside your body. So these angles aren't very big. That's a tiny angle. And then now what's going over here? Well, you've got a couple of bicep muscles here, the brachialis, the bicep. So let's put two of them in here. There's your bicep, one bicep. And then there's another one attached a little bit closer to your elbow. This end is your, so this end is your hand. And this is your elbow. And we're just interested in this forearm. So we've got that bicep muscle pulling. I mean, this is what holds your forearm horizontally. And then we also have the brachialis here. And these angles are different. This would be quite a big angle, like 80 degrees. And this would be a smaller angle here, maybe 70 degrees. And this one would be your brachialis. Okay. Now, notice how this brachioradialis, bicep, brachialis, they're all sort of pulling your forearm into your elbow. So the joint has to react to that. And those are called stabilizing forces, actually, the horizontal component. But your elbow has to react. I better move this over a little bit so I've got more room for your elbow. Okay, so here's your elbow joint. And your elbow will react with what are called joint reaction forces. And so there'll be a horizontal joint reaction force counteracting all those muscles trying to pull your forearm into your elbow. So this is called the horizontal joint reaction force. And that will only be big enough to keep your forearm from cramming itself through your elbow joint. So this will adapt depending on what you're doing. So horizontal joint reaction force. But also, it's when we start doing these analyses, we'll see that these bicep muscle forces are huge, much bigger than the weight of your forearm or the weight of this dumbbell. And so what has to happen is your upper arm has to exert a downward force here to counteract all these upward muscle forces. And this one is called the vertical joint reaction force. And so, and those are important because this is the stress that's being put on your joints by holding a weight in your hand. Okay, so you can see that that gets fairly complicated. There are a lot of forces there. And later on in the course, we're going to be doing a much more in-depth analysis of this by taking components and balancing forces or seeing which ones are out of balance and what causes this motion. Okay, so one more example that you have in your book that you're going to have to do is when you have your femur and then your tibia here. So this is your knee. And then you've got your patella, this little thing here, which is being pulled by your quadricep tendon, which is attached to your quadricep muscle. And then you've got the patellar tendon attaching it to the tibia. I'm not sure if that's called patellar tendon or just patella tendon. But anyways, definitely a force in that direction. So what we're analyzing here is the patella. Now, there's contact here between the femur and the patella, so that would be a contact force, perpendicular to however those two things rub against each other. And so if we were to reduce the patella to a box, we've got an upward force due to the quadricep tendon. We've got a force down at an angle, and it depends what your knee angle is, what that angle there is. And then we've got this contact force, something like that. Okay, so that would be the free body diagram for the patella itself. Okay, I think that's enough for now.